In most real-world situations, we will not be dealing with populations that can be described using standard normal. Instead, they might be described with a population mean that is not equal to 0 or a standard deviation that is not equal to 1. These distributions, while still being bell-shaped and symmetrical, are just described as being non-standard. So what we'll need to do to find probabilities under our non-standard normal curve will be to convert that population mean and our x values into 0 and a z value. Recall that z-scores are equal to our x value minus that population mean divided by standard deviation. So a z-score, in a way, describes how many standard deviations a value falls away from the mean. Of course, thanks to functions like Excel's norm.dist, we don't necessarily need to convert between x values and z-scores, but it's good practice to be able to do so in case you are given a table of z-scores. Let's take a look at an example. The average human body temperature is 98.2 degrees Fahrenheit. Now, the standard deviation is 0.62 degrees Fahrenheit. So this is helping us to describe that spread around the mean. Suppose we want to know what proportion of the population has a body temperature above 99 degrees Fahrenheit. In this case, we want to know the area to the right. We can do this by converting the value to a z-score and then finding that value in our table of standard normal z-scores that gives us the cumulative area under the curve to the left of that z-score. And then looking up the corresponding values from a table that gives us cumulative area under the curve. So we can start out by plugging in our numbers and subtracting the population mean from our value x and then dividing by our standard deviation. Now, I've left off the units here, but it is good practice to always include your units. Rounded to 2 decimal places, our z-score is 1.29. Basically, we've converted what we had to a standard normal distribution, where our z value is 1.29, and now we can use our table to look up the area under the curve. That table doesn't list the area to the right of a z-score, but instead the area under the curve to the left. And the area to the left of our z value is 0.9015, which means that the area under the curve to the right of our z-score is 0.0985. Remember, we rounded our z-score to 2 decimal places. This is standard practice, but it's a little bit of a limitation when using these tables. If we use Microsoft Excel to calculate this area under the curve, we'll undoubtedly get a slightly different answer because it will be using unrounded values. You can consider the table to be a great approximation and a useful tool to do this kind of thing by hand, but ideally, we should be working with unrounded values. Let's say I'd like to be able to use these probability distributions to identify a significantly high body temperature. When we talk about finding a significantly high value, we mean that the probability of x or greater should be less than or equal to 0.05. So the area to the right of that value is going to represent 5% of the values. Remember, when we're looking up the area under the curve with our table, we're looking at the cumulative distribution from the left. In this case, 0.950. For the area under the curve to be 0.950, the z-score is 1.645. And because this is our threshold for significance, we call this a critical value. So to identify our significantly high temperatures, we can rearrange our equation x minus mu over sigma. Rearranging the formula for x, we have sigma z plus the mean mu. Plugging in our value from before, where the standard deviation is 0.62 degrees Fahrenheit, times our z-score, that critical value of 1.645, plus that mu, population mean, 98.2. Again, leaving off units just for convenience in this video, gives us 99.21299, rounding to 99.2 degrees Fahrenheit. So if your body temperature is above 99.2 degrees Fahrenheit, you have a significantly high body temperature, which also means there's a 95% likelihood that your statistics professor will excuse you from class. Let's try doing some calculations in Microsoft Excel using that norm.dist, that normal distribution function. Let's start by actually plotting a normal distribution for that body temperature data. Now let's apply our norm.dist function, that normal distribution function, in Excel to visualize that body temperature data. So I want to start out by writing out those population parameters. The mean mu is 98.2 degrees Fahrenheit, and that standard deviation sigma is 0.62 degrees Fahrenheit. Now, when we create our standard distribution, we'll start out 4 standard deviations below the mean, and we'll go in increments of 0.5 all the way up to 4 standard deviations above the mean. So these are just z-scores of -4 to 4 when we're working with a standard normal curve, where the mean would be 0 and the standard deviation would be 1. However, with the body temperature data, we're going to need these z-scores to be converted into values of actual body temperature so we can make sense out of what's happening. And we also need some value y, which is the height of the curve for any given point along that x-axis. And this is referred to as the probability density function. So let's go through this. Remember, a z-score is equal to x minus mu divided by sigma. Rearranging to solve for x, we have standard deviation sigma, and I'm going to do function f4 because we're going to lock that parameter into place, multiplied by z plus the mean. And I'm also going to lock the mean in place because what I'd like to do is copy this formula down and only have that value for the z-score change. So now I can click to drag, or I can double click to copy that down. And now we have our range of values from -4 to +4 in terms of standard deviations above or below the mean. So we still need what will be the height of the bell curve at different points along x. To get this value, we use the norm.distribution function, first specifying that value for x, then specifying the mean. In this case, the mean is 98.2. So when I select 98.2, I'm again going to hit function F4 to double dollar sign lock that cell so it does not change when I copy this formula down. Then we specify the standard deviation. I'll also lock that one. And now, instead of doing true, which is that cumulative area under the curve from the left, we actually want to specify false, which is that mass probability function. And that will give us that height at any point x. So we can click enter and then drag that formula down. Next, we might select our data set, our array of x and y values. We can go to insert, and then we're going to find a scatter plot. And I think so it looks pretty. We'll use the scatter with smooth lines. Now we can see our graph, and I'm going to quickly add some axis titles because I want to make sure it's obvious that this is showing this distribution of body temperature, specifically body temperature in degrees Fahrenheit. So now we can see a nice normal distribution here. So a question we have, I think that we were doing in the assignment, was what if at what point along this curve might a body temperature be considered significantly high or significantly low? Now let's say again, we'd like to find a value that would be considered significantly high, a statistically significant fever, you might say. So to do this, we don't need to convert between z and x values again because we're using wonderful computers. What we're going to do is use the norm.inverse function because we want to find that area to the left of the curve being 0.95, right? Where a significantly high value would be less than 5% of values under that curve. So since we always go from the left, we're looking for that temperature when there's 95% of values below it. So now for the mean, we're going to specify 98.2. And we are going to specify 0.62 for that standard deviation. And when we press enter, we get a value of 99.2 when rounded. Notice that this is the same value that we got when we did this by hand.